Hello, everyone. Yeah, it's so nice to see everyone here and welcome you to coming to our talks. Yeah, I'm CK. It's my second time to Black Hat, but last time because of COVID-19, we cannot come here for presentation. So it's a very exciting and a little nervous here. Yeah. So today our topic is IRonMAN, interpretable instant inspector based on large-scale language model and association mining. Yeah, in our work, we're trying to integrate the most popular and novelty LLM model. And in the same time, we combine the traditional association mining to assist our analysts to handle the incident response. Yeah, because we like to use the large language model, but however, it's a black box. So we use a more traditional association mining to complement this problem to give our analysts more explainable result about our analysis. So this is today's online, and our research is composed of two parts, from the cybersecurity part and the data science part. So the first part will go through our motivation and our problem from the security perspective. And then we will move to our data science part. So we will introduce our two systems, Command GPT and IRonMAN. And then we'll go to the evaluation to show you how we can use this system and to analyze the real-world incident. And finally, we will give a very briefly takeaway. Okay, before we go into our topic, let me quickly introduce ourselves. Yeah, in our research member, we have 3 members in this research, and the first author is Eric Huang. Yeah, and he's our senior data scientist at SciCraft. And he has very talent in the data science and has published several papers in top machine learning conference like CVPR and IJCNN. And his research is focused on large-scale multifactorial anomaly detection, automatic AD security analysis, and user behavior retrieval. Yeah. And next is our leader of our machine learning team, George Yang. Yeah. And he's our data science director and focuses on building the distributed large-scale machine learning system to help us to handle the cybersecurity problem here. And he also trying to adopting a large-scale model, large language model, to handle the security problem. And he loves to sharing his experience and his research. So he has been a speaker in the CyberSec, SecCom, PyCon Taiwan, and PyCon Japan. And he's also the CTF player. Yeah, and you can just call me CK, and I'm responsible for organize our research team in SciCraft. And I'm also a retired CTF player, so my team, Bamboo Fox, is now the team TWM48, and they will also participate in the DEF CON final in a few days later. And yeah, we hope they can get a good grade in the CTF. And I'm also a member of Association of Hacker in Taiwan. Yeah, every year we will hold our conference event and the CTF event. Yeah, I think our CTF event is one of the most important top CTF content in the world. So if you want to enjoy traveling to Taiwan and different kind of hacker culture, welcome to join our event. Okay, so now come back to our research. So our research is start from Taiwan. Yeah. Maybe many of you already know that Taiwan has a very special position in the world. Due to the geopolitics, Taiwan has a special relationship to China, and it's always at the forefront of cyber threat. Yeah. So we always collect the first-hand intelligence, like the new exploit and new malware, when we analyze the attack targeting Taiwan. And we have closely monitored numerous cyber attacks, especially for those come from China. So about 10 years ago, our boss, they present in Black Hat. Their topic is hunting the shadow. They're trying to analyze the back-end infra of the China threat actor. And at the same time, they also analyze how these people, this threat actor, can work together to organize the whole attack targeting Taiwan. Yeah, and 3 years ago, we also have the Operation Chimera. We disclosed the cyber attack targeting Taiwan semiconductor industry. Yeah, so this shows that Taiwan is always very important during the cyber war. So today we are more talking about is not our finding, is how we can monitor this attack from the threat actor. So every day we will monitor more than 200 million events from our visibility, from government, from financial sector, and from some semiconductor vendors. So to handle this large amount of events, it's trivial that we cannot analyze by the human. So some automatic or machine learning mechanism is indispensable for us to inspect the attack. Yeah. In the same time, we also need to provide the analyst reliable weapon to recognize which command, which event is related to the attack, and triage the event and help them to do response and reasoning what happened. Yeah. And in today's presentation, we somehow narrow down our scope. We focus on the process creation event and with the command line information. Why we choose this direction? Because command line information contain a lot of intelligence that can help us to identify the attacker. But also because the command line has a rich semantic information and a flexible format. So it's not easy task. It's one of the most complicated problems when we analyze the event log. But however, I think our research has the potential to migrate and apply to other kind of event log. Okay, before we go deeper to explain the command line problem, let's do some exercise. Yeah, I want to have some interaction between us. So in here we have 5 commands in the screen. Yeah, and I want to ask which command line can correctly print out the computer name. Yeah, I give you 5 seconds to see this command. 5, 4, 3, 2, 1. Okay, if you think the first one can print out the computer name, please raise your hand. Anyone? Okay, I see some people. Okay, and the second one. Okay, the third one. Yeah, thank you so much. And the fourth one. Okay, and the last one. Okay, I already see some people has raised their hand multiple times. That means you are correct. Yeah, because in fact these 5 commands can print out the host name. Somehow the last one is a little tricky because we cut out the last part of the PowerShell. Yeah, but what I want to highlight here is that even so a very simple thing like the host name, we will have a lot of different ways to represent it. So recognizing the command line functionality is not an easy task. Not to mention how to develop or write in the detection rule. So let's bring out our today's challenge. So to analyze command line, the first challenge is a syntactic problem. First thing we would like to, can we parse the command line correctly and precisely? But however, it's not that easy. People may think, why not we just use the command line parser to parse the command line and everything will go well. But however, in many cases, we are not only deal with the Microsoft's built-in program. In a lot of cases, we have a third-party application software and some program developed by the customer themselves. So for this customized software, the parameter format is unknown for us. Yeah. For example, here the Q1. Yeah, it's an AV dump. This is a benign program in the antivirus software, but however, the threat actor can abuse it to dump the process memory. Yeah, so this is command that we're hunting in the wild. So in this case, we doesn't know anything about the format. Yeah, and much more difficult thing is that some parameter they may be encoding in some specified data format, like the JSON. And some programs may have their own query language, like the WMI, LDAP, and SQL. And moreover, some parameter you can directly put the whole program inside, like the Python, PowerShell, and .NET. So today, if I want to parse the command line correctly, it's not only a problem of command line itself. We need to parse in many different data format and query language, or even the whole language. So it's infeasible to implement a command line parser to finish all the things. And much more difficult is that the attacker will try to obfuscate their command and make you hard to analysis. Yeah. So there has dozens of a command obfuscation technique is available. Yeah. So for example, the Q2 here, you can see the attacker can put some special character here and make the appearance different. So you cannot easily to build a parser or to build a pattern. The attacker is easy to evade this method. Okay. Okay, so we have the syntactic problem. And then next, we also have the semantic problem. Yeah. Can we build a system that can realize what happened in the command? Here we point out two questions. The first one is that you can see here, the Q3, we have the 3 scheduled task keyword here. But however, every keyword is a different meaning. The first one is a command. The second one is a name of the task. And the third one is a file name. So you can see, even so the same keyword may have a different meaning. So we can directly use the pattern and keyword to match it. And also, on the other hand, we have a different keyword but have the same meaning, like the Q4 here. The first line is a normal mimikatz command. But however, the second one, even so it's mimikatz, if we observe the whole command line, it's more like the RG command, like trying to dump the directory. Yeah. And the third one, even so its name is a Mersoft, but however, depend on whole command line argument, you are more likely to be a mimikatz. So in this case, we can see, even so the first one and the third one, they are different keywords but have the same meaning. So this makes we analyze command line much more difficult. And if so, we can conquer these two questions. We will have the other problem lies the contextual problem. If we're dealing with an instance, we are not only need to analyze a single command, we need to analyze maybe 10s or 20s command in the same time. Yeah. So could we identify significant token based on the contextual information? For example, in the left-hand side is a command that in instant. But however, some command is useless, is not related to the attack. Yeah, and maybe it's just typing by their IT member, or maybe it's just noisy. Yeah. And the second is that when we, for example, for the p.exe and m.exe, it doesn't have any meaning if we see the command itself. But however, if we put all the command line together, then the meaning of this token are emerging. Yeah. So we can see the p.exe is downloaded by the director via the bsetmin and executed to raise their privilege. And m.exe is possibly a mimikatz used to dump the credential. And afterward, the credential is be discovered by the director. So some information, some keyword doesn't have any meaning if we see a command line itself. But if we put everything together, he have a special meaning. That's also the one thing that we want to track in. So for both three challenge, it's infeasible to manually develop the detection rule. So we have the syntactic problem, semantic problem, and contextual problem. And we also have an explanation issue, because every time we need to explain to our customer why we believe this is an attack and what happened. We need to have a evidence and a reason for them. And how about the problem if we, every day we may have hundreds of malicious events a day? This made the problem much more difficult. So of course, we need a automatic method that can help us to detect the malicious command line without any rule or regular expression. So that's why we start this research. And we built a system, original, we called it the IRonMAN. But however, very soon we realized it may have some problem if we use this name. Yeah, so we changed our name into the IRonMAN. And this name can also represent that we can help the man, our analyst, to do the IR. So I think it's a very good name and very close represent what we are doing. Okay. So next, let me go to more detail about our model, our algorithm. So let's unleash the AI's enchanting magic. So the next part, our data science, Eric, will help us to go to more deeper and introduce every detail of our model. So let's welcome Eric here. Here. Yeah.
Okay, thanks, CK. And hello, everyone. My name is Eric, and I will introduce the IRonMAN in detail. Okay, and the story begins from the SecCon in February of this year. And command line embedding model CMD-GPT was introduced. And it underwent thousands of command lines with self-supervised training technique. So thanks to the extensive command line training data, CMD-GPT is empowered to embed different command lines into a unified feature space, leveraging their contextual information rather than just relying on their wording. And in our experiment, CMD-GPT's performance is comparable to OpenAI's embedding API on our command line testing data set. So with CMD-GPT, we can measure different command lines similarity easily, and we can also query the similar command line from our malicious history database. And for example, here are two command lines. And although they use different executable file names, CMD-GPT still assigns a very high similarity to them because they use the same argument here. And this embedding ability can also help a daily incident investigation as well. For example, presented a new incident, we can first cluster the old command line of this new incident and assign each cluster with its corresponding behavior and construct the timeline graph as the figure. And this enables our analytics can get a comprehensive overview of the incident quickly, facilitating further in-depth analysis and informed decision-making. But although CMD-GPT demonstrates very powerful command line embedding ability to us, but it still falls short of meeting all of our needs. For example, we are unable to know why these command lines are similar, why these command lines are clustered together in the same group. So in this work, we will aim to, So for such interpretability, we believe that the traditional mining algorithm is the one of the approach can provide a very easily understandable result to us, because most of the traditional mining algorithm depends on the simple threshold filtering rules. And in our experiment, traditional mining algorithm mine the significant tokens based on the two simple rules. The first is the frequency with the same cluster, and the other is the rarity in other cluster. And here we will demonstrate a very simple example to show how traditional mining algorithms mine the significant tokens with the two rules. And here are two cluster 1 and cluster 2. And the objective here is we want to mine the significant reason for why these two command lines are clustered in the cluster 1. And we have identified two candidate reasons, token echo and token mimicast.exe. Let's start from the token echo. We can check whether it follows the rule 1. And the token echo appears in two command lines in the cluster 1 that satisfying the rule 1. But when we check for the rule 2, we will find that the token echo also appears in the both command lines in the cluster 2, which contracted the rule 2. So we can move on to the second token mimicast.exe. And we found that the mimicast.exe satisfies the rule 1 frequency with the same cluster and the second rule relative in our cluster at the same time. So we can confidently determine that the token mimicast.exe is the significant token for the cluster 1 in this case. But although this traditional mining algorithm can provide a very easily understandable result based on the simple threshold filtering scheme, but it is susceptible to even the slight change in the command line. For example, if we modify the token mimicast.exe in the one command line with the cluster 1 to the token mimicast.exe, and the first rule, frequency with the same cluster, will no longer be satisfied. And so in this work, the question we want to address is, can we analyze the incident, analyze the command line from the perspective of context as the CMD-GPT does, while also providing very easily understandable result as traditional mining algorithm. And based on this motivation, we propose the IRonMAN here, an interpretable incident expector. And IRonMAN has 2 key properties. The first is that IRonMAN can investigate the incident from the context perspective based on the CMD-GPT. And next is IRonMAN can mine the significant token directly in the feature space. And this allowed IRonMAN can overcome the limitation of traditional mining algorithm we mentioned above. And this significant token can also serve as a strong and understandable evidence to support our investigation result. And given a malicious command line to IRonMAN can help us to mine the significant token of this malicious command line. And this significant token can be transferred into the sigma rule or the blacklist further to help our SOC analyze. And this is a big picture of the IRonMAN. And present a new incident. We first will collect all command line logs from our EDR engine, and next we will embed all command line log into a unified feature space using CMD-GPT. And in this feature space, there are some other command line, for example, APT campaigns malicious command line and some rating campaigns malicious command line we collect before. So we can directly in the unified feature space to mining and compare with this malicious command line to mine the significant token for this new incidence command line. And in our case, there are hundreds of malicious events or command line per day. But with IRonMAN, we can mine a significant token for all of these malicious command line easily. And it's worth to note that IRonMAN do not adopt any exact match mechanism like sigma rule or regular expression in our entire IR analysis pipeline. Okay, and here's the introduction part. And next, we will talk about how IRonMAN mine the significant token in the feature space directly. And to mine a significant token, the crucial task is to evaluate the token's importances. And in our experiment, we found that we can measure the token's importances by observing the similarity change when we remove the token from the command line. And for example, here are 2 command lines, and both are correlated with mimicast.exe. And if we calculate the similarity between these 2 command lines, we will get the similarity is 0.901. And next, if we want to evaluate the token mimicast.exe's importances, we can remove this token from the command line and calculate the similarity again. And I'm doing so, we will observe a drop in similarity from 0.901 to 0.843, indicating a loss of 0.058. And this process can also be adapted to different tokens like token echo and token system32. And after calculating all importance score for all our tokens, we can find that the token mimicast exhibit the largest similarity loss in this case. This result also indicates the mimicast.exe is the significant token for the similarity between these 2 command lines. And so for now, we have approach can evaluate tokens' importances. But the other question is, how do we tokenize the command line appropriately? And this test is particular challenge because, and especially for command line, because of the command line's flexibility syntax and the flexibility structure. So here's an example. It's a very simple command line. How do we tokenize this command line into the meaningful pieces? And we believe the first approach we will try is divided by the space. But this will produce some unexpected token. For example, the program file x86 directory is divided into 3 different tokens. And the x86 is even grouped with the text.exe and the argument gogo in this case. And we think that if we directly evaluate the importance score with this unexpected token, it will lead to some inaccuracy for our significant token mining assessment. So the next step, we must well try to design a very good regular expression to help us to tokenize this command line. But in our experiment, crafting a good regular command line regular expression for all command line is a non-trivial and time-consuming task. So we think we need a more straightforward tokenizer in here. And before we decide a good tokenizer, we must first define what qualifies as a good token. And we believe that ideal token should represent the complete meaning by itself. For example, a token should represent the entire file name, entire directory name, or entire argument. So for the simple example command line, we believe the ideal token set will look like this token. And to ensure we can tokenize each command line into appropriate meaningful pieces, we propose a meaningful tokenizer to help do this job. And meaningful tokenizer is a command line tokenization specific language model. And to train this model, we first collect about 4,000 command line and their corresponding ideal token set. And next, we fine-tune an open source pre-trained language model on this trained data with the castle objected. So after training the meaningful tokenizer, given a different command line, meaningful tokenizer can help us to token this command line into the ideal token set in just one forward pass. And here's the actual example for the meaningful tokenizer. Given this complicated command line, the meaningful tokenizer can still help us to tokenize this command line to the meaningful piece accurately. And for now, we have an approach can evaluate the token's importances, and we also have meaningful tokenizer can help us to tokenize different command line into the meaningful pieces. And next, we can start to mine the significant token in the feature space. And I will show you how IRonMAN mine a significant token with a very simple example here. So we just take one query command line to demonstrate the mining algorithm. And note that this mining algorithm can be extended to multiple command line or a cluster of command line easily. And the first step, if we have a query command line, we should embed the command line into an embedding vector using CMD-GPT and query the similar incident or query the similar command line from our malicious command database. And in this case, we can find there are 3 incidents has similar command line with the query command line. And next, we can expand the incident 3, and we will observe there are 2 command lines are similar to the query command line here. And to mine the significant token of query command line, we should tokenize this command line using our meaningful tokenizer first. And after tokenizing, we will get this token. So with this token, we can calculate the importance score between all tokens and each command line in the incident 3. For example, we can first calculate the importance score between all tokens and the first command line in the incident 3, and keep going for the second command line. And after calculating all important score, we can leverage the concept of traditional mining algorithm here to adopt a threshold filter to get the significant token for the incident 3. And note that we apply this threshold filtering on the important scroll instead of the token directly, which allows IRonMAN can overcome the limitation of the traditional mining algorithm we mentioned earlier. And only the token has certain degree of importance score for a certain proportion command life in the incident 3 will be retained. So this significant token can also serve as a strong and understandable evidence for our investigation result. And this process can also be adapted to different incidents. For example, incident 1, incident 2, and incident 3 to mine a different significant token for different incidents here. So we should apply one more threshold filtering here to get the true significant token of the query command line. And the significant token of the query command line here has the positive impact for the most command line in the most incident here. Okay, and that's all about how IRonMAN mine the significant token in the feature spec directory. And next, my colleague George will demonstrate some experiment results about our testing data and our real-world data. Okay, thank you.
Hi there, I'm George. So thank you, Eric, for his very detailed introduction to our system and our work. So in this part, I will start to introduce how our experiment result is. So the first thing is that, as you can imagine, the meaningful tokenizer is really important to our system. So the first thing we want to test is how it performs. So in this case, we manually select 400 different types of command line and ask our in-house security analyst to tokenize it and also label it for us as a ground truth. And here is the two different types of tokenizer. The first is the space tokenizer, and the second will be our proposed meaningful tokenizers. And the metric we are measuring is using the intersection of the union, so which basically meaning that how many produced tokenized tokens are matched with the one labeled by our expert. So as you can see in the figure, our meaningful tokenizer is about 20% much better than the space tokenizer, and only with about less than 5% of the overhead in the computation. And we even run this experiment on the NVIDIA 3090, so you don't need to have a very fancy like A100 or even H100. And also, I know that this type of small-scale testing would be very boring for you. So we actually apply it on a real-world scenario. So about 2 months ago, one of our customers is actually having a red team exercise. So this customer had about 5,000 endpoints at the moment. So let's look up how our IRonMAN performs. So let's look at the recall first. So during the 3 weeks of the red team exercise, there were 38 endpoints were breached by the red team. And among all these 38 endpoints, our system our expert is able to identify there are 257 malicious commands as a ground truth. So how IRonMAN works, we actually perform quite well. So actually, we only miss 8 command lines out of 257 commands. And in regarding to the precision, during this 3 weeks exercise, we actually collect about 7.3 million command lines from these specific customers. And our system is able to flag 291 commands as a malicious command. And we only miss about 42 false positive command as a malicious one. So I would say the result is quite promising, even on the real world scenario. So let's recall back to from the very beginning, from the CK's part. So he threw out some challenges to you. So how our system is actually working on these challenges. So the first challenge will be the synthetic problem. So actually, even with the unknown or unseen files or the exclusions, we are still able to cut the significant token out of it. And we are still able to perform like the similarity testing or the cross out of it. And for the another example is that even these two commands look completely different, and with the obfuscation, they are basically doing the same thing. It's just remove the shadow volume from your Windows machines. So by applying our IRonMAN system on it, we are still very confident, and we can perform very well to cluster these commands together because they have the same intention. So this is another good part for our system. And for the second challenge would be the semantic problem. So for example, the command that CK gave you is that this one. So we got 3 scheduled tasks in this command, which token would be the most important one for the security analyst. So in the traditional way, it's really hard for the traditional algorithm to tell that. But in our system, we are able to precisely tell you which token is the most significant one with the significant token scores. And for the final example is that the mimicast. So we change the mimicast file name, or we deliberately change the reg.exe to mimicast, and we are trying to see, okay, if our system is able to tell the difference between these 3 commands. So for the first example, even though it's all called a mimicast, but by our system, we are able to tell because by the format it is, and also the argument itself, it can clearly show you they are not that similar. When comparing to the second part, even the argument is different. The execution file name is different. Our system is precisely tell you, okay, it's a work. They are very, very similar, and the security expert should pay more attention to it. So I know talk is cheap, and we also always want to show some code. So we actually built up a demo site for you guys. So please take a picture on this slide, and here's our demo site. It's at IRonMAN.scikit.ai. So in this website, you are able to just follow very simple process, a very simple step, and we'll provide you a very simple PowerScript shell to collect your comments, and you just upload it to it. And then after just a few minutes, and you are able to receive an email link, open it. I promise you won't be a phishing email, so it will be safe. So you just open it, you can see this very beautiful web page. It will precisely tell you the severity of your input command line, and also will flag out all the significant tokens on your command lines by the colors. So as a security expert or analyst, it's very easy for you to just tell it by the colors. And the best thing is about our demo site is that we also provide a functionality that you can actually export your significant token to the Sigma rules. So once you got your Sigma rules, you can easily compile these rules to all your existing SIEM systems, and to help you to hunt more future command lines. So that's pretty much everything, and here's our final takeaway. So the first thing working on this project, I think the most important thing is that we think understand the nature of your command line nature of your data is very important, because a lot of people will say, okay, command lines just look like a bunch of very long sentences. Why don't we just apply the large language model and deal with it? And the reality is that it's really, really hard to get a really good result from it. So domain knowledge, especially when you're trying to apply this type of large language model on your field, please always remember, ask the security expert to incorporate with them, with their knowledge, and will help you to achieve much, much better result. And the second thing is that our work is clearly show you that there are strong evidence that malicious command line, especially for many different threat actors, they will have the very similar and significant tokens. So it's really easy to utilize the system like this to identify this, and also you can transfer it into the schema rule to hunt the future attack. And the last point would be, we actually find, by this research, we actually find there are many opportunities on the command line research. So we encourage your guys to explore in this area, for example, like the command line correlations or the smart search within the command line. And lastly, and please don't forget to take the picture about our slide and especially the demo slide link, and give it a try. And we are more than happy to hear the result from you guys. Thank you, guys. I think we don't have time for a question, but we will add the retro room. So if you guys have more questions, we are more than happy to answer it. Thank you.